Dear ladies and gentlemen, good afternoon. Whilst the public attention is attracted by the COVID-19 pandemic, we observe only limited impact of the curfews around the globe on greenhouse gas emission. So there is no reason to stop thinking which vectors can bring renewable energies into the transportation sector to stop it from releasing fossil carbon into the atmosphere. I would like to thank my co-authors for their support to this presentation. Here is a brief overview of the content of my speech. After the motivation, I will introduce possible vectors to bring renewable energy to the transportation system. Thereafter, I will present 3 example projects dealing with sustainable energy for mobility. Because further research is needed in this field, I will briefly discuss the funding situation and then conclude. Since the Industrial Revolution drives our greed for energy, our civilization continued burning fossil coal, oil and gas. Scientists started warning us of climate change already more than 100 years ago, but we kept releasing CO2 in the atmosphere where it converts our planet to a greenhouse. Despite all warnings, no mitigating action was taken for a century, and temperatures are increasing. The last decade saw CO2 concentrations skyrocketing to levels like 3 to 5 million years ago, when the sea level was up to 20 meters higher. Although water level follows temperature with a delay, this is bad news for today's metropoles on the coastlines like New York, Hamburg and Shanghai. The global temperature anomaly map of the months January to March of this year shows a scary warmth in the Eurasian permafrost regions. The heat goes on, reaching 38 degrees at the polar circle recently. In Siberia, millions of hectares are on fire. Permafrost is melting, bacteria convert biomass that was conserved in the ice for 10,000s of years to methane and release it into the air. Methane is 25 times more effective in global warming than CO2. We are close to the tipping point. Instead of continuing to exhaust our CO2 budget for the 1.5 degree target at the same or higher pace than before, we must take strong action to stop using fossil energy carriers and use renewables instead to become more sustainable. Sustainable. Many people talk about sustainability today, but who really knows the meaning of this word? Wikipedia defines it as the ability to exist constantly, while in the 21st century it refers generally to the capacity for the biosphere and human civilization to coexist. And Merriam-Webster's dictionary defines it as a method of harvesting or using a resource so that the resource is not depleted or permanently damaged. If we take this really seriously, we have an awful lot to do to make sustainability really happen. One of the most important factors to achieving a more sustainable mobility is using sustainable energy in any possible way. This includes water, wind, solar and geothermal energy. Taking sustainability serious, we shall avoid any energy carrier that we must drill or dig for. That means fossil carbon like oil, gas and coal, but also uranium. We can use renewable electricity in electric powertrains and machinery, whether stored in batteries on board or from overhead trolley lines, for example in rail applications. Renewable energy can be used for electrolysis, creating hydrogen that is used for fuel cells and also for internal combustion engines. Methane from biological waste that would otherwise end up in landfills can be used in internal combustion engines. Bio-to-liquid fuels from organic waste can be upgraded with green hydrogen for a larger range of ICE applications. And lastly, power-to-liquid and/or bio-to-liquid fuels can be used in plug-in hybrids on ICE for long distances, while these cars or vehicles could run locally on electricity emission-free. The most obvious is using renewable electricity in battery electric vehicles. Our Sevolver project aims at right-sizing components of electric vehicles, among others the battery. Why that? The public keeps criticizing BEVs for their short range, but ever increasing the battery size is not sustainable. Mining and processing of raw materials and the energy consumed in the production chain have a significant footprint. Therefore, Sevolver aims at saving raw material and cost, while maintaining an acceptable time for traveling. To demonstrate that this does not have an impact on the traveling comfort, we take the challenge of completing a fictive travel of 700 kilometers length, like, for example, from Stuttgart to Venice. However, our stops for charging shall not extend the trip time by more than 1 additional hour over the trip with a conventional car. The assumptions are, for simplicity, an average speed of 100 kilometers per hour, and with the conventional car, a 15 minutes bio stop. So the entire reference trip time is 7 hours 15 minutes. This trip with the conventional car is shown here. The easy approach for this trip with a battery electric vehicle is using a large 90 kilowatt-hours battery. We assume a power consumption of 200 watt-hours per kilometer, the battery full at the start and depleted to 5% SOC at the destination. When the battery is down to 5%, we recharge at 1.5 C up to a maximum of 80% or less if less is needed. When charging, we assume additional 5 minutes handling time for plugging and payment. One single 30 minutes charging stop is enough. We finish just 17 minutes after the conventional car, so that's not too bad. With a 40% smaller battery of 54 kilowatt hours, we must charge earlier and more often. A third charging stop just before arrival is very annoying. With a total of 80 minutes breaks, the trip takes 65 minutes longer and we lose the challenge. So how can we do better? We start with reducing the energy consumption of the vehicle. A smart navigation system, eco-routing, looks for the least energy-consuming route. It considers slopes, weather, traffic conditions. The eco-driving cruise control keeps the car running smoothly, avoiding stop-and-go situations as best as possible. An integral thermal management, including battery, electronics, and cabin ventilation, saves energy, and dimensioning hardware fit for purpose saves weight and losses. Altogether, we modestly assume 10% less power consumption in this example. Further, enabling a charging rate of 2.5 C instead of 1.5 C reduces the charging time, and assuring the availability of a charging point upon arrival by pre-booking and an automatic payment reduces handling time, so stops become shorter. Less power consumption kills the third charging stop, and the charging breaks shrink from 35 to 20 minutes each. The trip is now only 25 minutes longer than with the conventional car, and we win the challenge. And because of 2 breaks, you feel less exhausted upon arrival in Venice. So that is how you can travel with an acceptable time and comfort long distances with a rather cheap battery electric vehicle that you would normally buy for urban and peri-urban use. I should mention that the Sevolver project is one of the 7 projects of the Evolve cluster, all of them coming from the 2018 Horizon 2020 Green Vehicles Call. They all address the improved usability and efficiency of battery electric vehicles. For more information, please follow the link or find us on Twitter and LinkedIn. But using renewable energy in mobility is not restricted to the direct use of electricity. Fuels enable longer range and less weight. FEV is involved or has been involved in a number of research and innovation projects, dealing with eco-friendly fuels and their usage. I would like to give you some information about the projects ReadyFuel and C3 Mobility that are coordinated by FEV. The ReadyFuel project, with funding from the EU Horizon 2020 Secure, Clean and Efficient Energy Programme, investigates new ways to create sustainable, affordable biofuels for clean combustion in motor vehicles. The process starts with anaerobic pyrolysis of biomass, creating biosyn gas that is further processed in a Fischer-Tropsch plant to synthetic crude. The stoichiometry is adjusted by adding green hydrogen. The distillation splits this crude oil into different fractions. The heavy one with more than 11 Cs are hydrotreated to convert olefins into isoparaffins. The medium fraction from C5 to C10 undergoes a hydroformylation and hydrogenation process, resulting into alcohols for 6 to 10 C atoms chain length. The outcome of this process can be blended with diesel as EN590 compatible fuel that saves up to 65% net CO2 emissions. The target is to achieve production costs of about €1 per liter at a production rate of 25 kilotons per year. Our partners Neste Engineering Solutions and MOL will evaluate this. While ReadyFuel starts from biomass as a source of carbon, C3 Mobility, funded by the German Federal Ministry of Economic Affairs and Energy, looks into power-to-liquid fuels derived from green methanol. This means the methanol has to be produced from green hydrogen and carbon dioxide captured from some waste gas or from the atmosphere. Methanol can be further processed to many different chemicals. Our interests are the methanol-based fuels and the way how to use them optimally in industry and transport. The advantage of power-to-liquid fuels are related to their liquid state. Easy handling, you just pump it over instead of compressing and cooling, and a naturally high energy density per volume. The project aims at finding a cross-sector approach involving different economy sectors and evaluate the entire system and market introduction scenarios as well. The project investigates 3 different sources of CO2. Industrial areas where the CO2 can be extracted from waste gas containing high concentrations. Rural areas, for example biogas plants or alcohol fermentation, garbage incineration or from sewage treatment. And lastly, desert areas where there is plenty of solar energy for electrolysis and also for driving the energy-consuming plants for direct air capture. The power-to-fuel efficiency, that means the efficiency of converting electric power into heating value of fuel, consists of different efficiencies. There's the electrolysis efficiency, there's the energy spent for carbon capture, and the energy spent for the methanol synthesis. The graph gives you the tendencies found for the dependency of the power-to-fuel efficiency for methanol synthesis, depending on the efficiency of the electrolyzer when different technologies for carbon capture are employed. The blue lines indicate the range between the best and the worst case of using a membrane for carbon capture on an ammonia synthesis plant. The red line shows you the same for direct air capture based on sodium hydroxide absorption and regeneration, worst case and best case. The gray line indicates the overall efficiency trend for using an MEA, a monoethanol amine washing of CO2 applied at a cement plant. The green line shows you an example realized in an MEA pilot plant. The gray areas mark the ranges of electrolyzer efficiency commonly achieved with a PEM alkaline electrolyzer or with a solid oxide high-temperature electrolyzer respectively. The good news is that achieving a 60% overall power-to-methanol efficiency is actually a realistic value. These promising results call for continued research and innovation, and in particular, power-to-liquid fuels and their deployment must still be considered a pre-competitive research and development item for the coming years. This pie chart shows you the passenger car fleet in 2019 for the Euro 27 countries. The sectors represent the share of the vehicles of a certain age by their year of registration. The data is taken from the ASEA report Vehicles in Use Europe 2019. Obviously, 54% of the vehicles were older than 10 years. Each of the younger sectors contributes only between 4 and 5% to the fleet. The average age of cars amounts to 11.2 years. Commercial vehicles are still older, for example 12.9 years for medium and heavy-duty commercial vehicles. In several areas, their age exceeds 15 years, up to 21 years in some cases. With a grand total of 270 million vehicles of all classes, we can conclude that many vehicles with internal combustion engines will still be around way after the year 2030. The premature exchange of this fleet with electric vehicles would, however, exhaust a significant portion of our CO2 budget that we have in our 1.5-degree global warming budget. Therefore, we need to reduce the carbon footprint of the existing fleet while other green options ramp in. This takes a combination of carbon-neutral drop-in fuels, cost-efficient retrofitting of the existing vehicles to use new green fuels like hydrogen or methanol, for example. In the meantime, the provision of green energy must ramp up dramatically to cover the entire energy need, not just today's electricity sector. Defossilizing the fleet has the fastest and largest impact when we strive for carbon-neutral transportation. We must not forget the old vehicles. The European Green Deal aims at a climate-neutral European Union in 2050. Our carbon dioxide budget for the 1.5-degree target is running out. Time is running out as we continue emitting greenhouse gases. Europe must cooperate in acceleratedly developing new carbon-neutral mobility solutions, battery electric vehicles, fuel cell electric vehicles, all kinds of hybrid electric vehicles running on green fuels, for example, green methanol. We have to phase them in, while the carbon footprint of the existing fleet must also be reduced by providing non-fossil carbon-neutral fuels that are compatible to existing fuel norms. Further research and innovation by academia, research institutions and industry will require further financial support so that they can come to results as soon as possible and deploy them in the market. Now let us see what the European Commission prepares for us. In context of the European Green Deal, the European Commission is in the process to install a new partnership with the public side, 2.0, for Horizon Europe. It is the evolution of the very successful previous partnerships under Frame Programme 7 and Horizon 2020, the European Green Cars and Green Vehicle initiatives, respectively. 2.0 clearly aims at achieving a zero-emission road mobility system for people and goods. It supports the vision of a climate-neutral European Union by 2050, using 100% renewable energy for all types of road vehicles. The system approach shall ensure the interconnection and interoperability of different sectors between vehicles, logistics, energy, and infrastructure. By taking this systems approach, the 2.0 partnership has interfaced to several other research and innovation partnerships under the patronage of the European Commission. Green hydrogen is a carbon-neutral energy carrier of mobility indeed. The main partnership for this is Clean Hydrogen. This partnership was formerly known as Fuel Cell Hydrogen Joint Undertaking. Electronic equipment, sensors and microelectronics, cybersecurity and related components are developed in the continuation of Excel joint undertaking that now will be called KDT, Key Digital Technologies. And there are two totally new partnerships: CCAM for connected, collaborative and automated mobility, and batteries for, the name tells it, research on battery technologies. As an example how the interfaces are defined, I will show you the interaction of 2.0 with clean hydrogen and batteries on the next slide. The 2.0 partnership, with its role of integrating the different technologies from the other partnerships, takes the lead in defining research and innovation calls and topics whenever the vehicle or mobility-specific aspects are in focus. The Batteries partnership is responsible for the battery materials science, cell design and production technology, and standard battery modules on the one hand side, and also for the end-of-life processing on the other hand side. Vehicle-specific module designs and packs and their integration and use in the vehicle are in the scope of 2.0 partnership, where necessary in collaboration with the Batteries partnership. Analogously, 2.0 will deal with the integration of fuel cell systems and tanks in the vehicles, their use and interface with the infrastructure, fuel cell component development, but also large-scale deployment is in the responsibility of clean hydrogen. For light-duty vehicles, the focus of 2.0 is clearly on pure electric vehicles. Fuel cells and light-duty vehicles have been investigated by Fuel Cell Hydrogen Joint Undertaking in the past frame programs extensively. The application of fuel cells shall now focus on heavy-duty applications for long-distance transport like trucks, long-haul tractors and coaches, though synergies of heavy-duty developments with light-duty vehicles will be appreciated. To conclude, the long-lasting presence of internal combustion engine-propelled vehicles in the fleet today and in the future calls for the development of affordable carbon-neutral fuels as soon as possible. To become more sustainable, batteries need to be produced increasingly from recycled materials using green energy. As we lack green energy from domestic resources, we must import it, for example, from North Africa and Middle East. Pipelines for hydrogen and tank ships for green methanol or ammonia are appropriate for medium and long-distance transport of green energy stored in green fuels. Direct use of these e-fuels in mobility is probably more effective and more efficient than electrifying them for charging electric vehicles. The European Commission focuses its partnership for research and innovation funding on battery electric vehicles and fuel cell electric vehicles. But there is need for alternative research and innovation funding related to the production and for the usage of advanced biofuels and e-fuels in hybrid powertrains and in the existing fleet. Therefore, member states need to join for a coordinated funding of research and innovation like they did before in ERANET or Eureka, or by a multinational combination of national fundings to increase the efficiency and the environmental friendliness of powertrains with thermal engines that would run on carbon-neutral fuels. Carbon-neutral mobility requires the combination of powertrains fit for purpose. That means battery electric vehicles, fuel cell electric vehicles, and all kinds of hybrids with a clean combustion engine on board. On behalf of the authors, I would like to acknowledge the material that we adopted from the different sources here. And also I would like to point out to the disclaimer of the authorities named therein. Thank you very much. And this is my last slide, so thank you very much for your attention.